So hi everyone, my name is Conor, and I'm going to be talking about my research this summer at the UBC Laboratory for Atomic Imaging Research. It's in Scanning Probe Microscopy Lab in Apple. So first off, what is STM? It's a form of electron microscopy where you basically have a sharp tip that's scanning over a surface, and when they come within about an angstrom of each other or so, you get a non-zero probability of the electron tunneling through to the other side, either from the surface to the tip or the tip to the surface when there's a bias between them. And so this tunneling current changes as you scan across the surface, and you get an image based on that tunneling current. And then with STM luminescence, the electrons tunneling through, they may also not tunnel through elastically, they may lose energy along the way. This happens about every 1,000 or 100,000 or 10,000 times. And this loss of energy comes out as photons, which we can collect and analyze, and we can get some information on the optoelectronic properties. These are important for photovoltaics, as Alfred was just mentioning. And there are two types of emissions for STM luminescence. There's inelastic tunneling, which is just losing energy. And then there's also molecular fluorescence, which is if there's some molecule on the surface, the electron will tunnel into the molecule, lose energy within the molecule non-radiatively, and then emit a photon and keep tunneling. And so in order to have STM luminescence experiments, there's three things that need to be done, or three really important things that I did. There's the tip etching, which you need reproducible etching for these tips. They need to be incredibly sharp for this technique to work. And we did tungsten and silver for reasons I'll explain in just a second. There's the photon collection system. So once these photons are emitted, you need to be able to focus them into a spectrometer, you need to be able to collect them, analyze them, and such. And then you also need an incredibly low noise environment. And so this was just constructed in Apple this summer, and so I'm going to finish my talk about the new facility. And so with tip etching, the tips themselves are very rarely one atom in the ideal case. And so they're usually defined by the radius of curvature. In some pictures later, I'll explain exactly what that is. Less than about 200 nanometers is usable because there's some things that you can do, some manipulations you can use in order to get them to a good quality tip. But even if you have just basically a flat surface with one atom sticking through, you'll still get a beautiful image because the decay in tunneling probability is so large over even an angstrom. And you want these tips to have a plasmonic resonance, which is why we use silver, because silver will have this photon interaction about 1 in every 1,000 times, whereas tungsten, which is the standard for tip etching, has about 1 in every 10,000 times. And so the other thing is, when you're scanning something that's only one atom, you need a tip that's only one atom, or else you won't be able to resolve it. So the things you're resolving have to be larger than your tip. So the method we use is not the normal method that's supplied in the literature. We do use an electrolytic redox reaction, so basic chemistry. But instead of the meniscus method, which is on the show diagram, most tip etching is done where they just put the wire about 2 millimeters into solution and just etch in the meniscus of the solution. Whereas what we do is we immerse it much more in the solution, and then we cover it with Teflon. So we isolate the reaction to one small area. And then, as you can see on the bottom, the tip just basically drops off into the solution. It's kind of dark there. But it's a very, very simple system to use. And so in order to characterize these tips, I used a step-by-step process. And so the first two steps were both optical microscopes. There's an 8x stereo microscope, which is very good with depth of field. It's an amazing depth of field. And then the compound optical microscope has much more zoom, but not quite as good depth of field. And then if they look good under these two, I put them in a scanning electron microscope, and I can go up to about 500,000 times, but the resolution in 500,000 is never that good. I think this one's about 100,000. So the scale on that photograph is 200 nanometers. And then obviously the best way to figure out if something works in STM is to put it in an STM and see if it works. So my goals for the summer is to basically find a recipe for both silver and tungsten that gives reproducible sharp tips, and it's really simple and quick. And so the parameters that I varied the applied voltage and the voltage type, AC or DC. The gap size, so the gap in that, right here, was varied between about 0.3 millimeters and 1 millimeter. And then the other one was the electrolyte concentration. So the electrolyte for silver etching is KOH, potassium hydroxide, and that was varied between 1 and 3 molar. And the electrolyte for silver was citric acid, and that was about 40 or 50% weight by weight. And so I'm just going to show you guys some quick pictures of what I did. So that, first off, that's what can go wrong. So these tips are very, very difficult to use, to be careful with. If they touch anything, this happens. And so sometimes you get these beautiful spiral patterns. Sometimes you get hair. I don't really know what happened there, but these are some of the not so good tips, but still interesting to look at. And then some of my earlier successes. So this is where you can see what the radius of curvature is. It's just this, and so that's 150 nanometers, 50, 55, a little bit more than 50. And the only silver one out of those is the one on the bottom here. All these other three are tungsten. And so these are the earliest successes. As you can see, they're in the range that I wanted them to be. And then next we have these ones up here. You see that one? It's 50 nanometers. It's beautiful. 35. These are all in the range that I wanted. And this picture on the bottom is really interesting because, as you can see, it's the same tip taken with a primary collection and a backscatter. And so you can see this coating we're using the primary detector, but this coating disappears using backscatter. And so you can tell it's not the tip material, it's some kind of coating on it. And what we think it is, it's an oxide coating due to basically just me being sloppy. And so the results, the silver, the best tip I showed for silver was that one on the bottom. It's about 50 nanometers. And it wasn't reproducible at all, in neither in time nor in sharpness. Tungsten was. It was very reproducible. And so what we did a study on the gap size, so very dedicated study to try and figure out what the best gap size is. And the results are on the bottom of this projector, but the success rate was drastically increased when you got over 0.5 millimeters. It peaked at 89% for 0.7 millimeters, and the average radius of curvature for those tips was 30 nanometers, which is beautiful, plus or minus 10. So there's not a lot of deviation. And so the optic system, the photon collection system. You obviously need a system to collect the photons once they're emitted from the tunneling junction. And then you need to collimate them and focus them in the spectrometer. And so the system has components in the STM and outside the STM. The external components just hang off, basically just hang off one of the viewports. And there's a space issue that we have. So the spectrometer is 90 degrees to the viewport. So I can show you a picture in a second. And the system basically needs to have 4 degrees of freedom in order to properly focus the light, and properly guide it. So the challenges, there's very little space to work with. The external optics, we can't have them too heavy or they'll bend the chamber. And we really don't want to do that. The system needs to be lossless because, as I said earlier, this only happens 1 in every 1,000 electrons that go through, and the current that usually goes through is in like nanoamps or picoamps. So there's not a lot of photons to begin with. Then there needs to be a lot of micro adjustment because even a slight like micrometer change could potentially disturb the focusing. And we want to be able to avoid fiber coupling, so we want to be able to focus the light in space, but we also want to be able to focus onto a fiber if necessary, because it's just much easier. That's the initial design. It's been done before, so we based it on this system by Kaiser. And so this is the in situ part. There's a lens here to focus the light. This is the viewport, and then another lens outside, and then another lens. So these are basically just a telescope and refocus it, and then basically into the spectrometer here. And so our system, we don't have the beam splitter and collimator, and we're not possibly going to, we don't have the beam splitter or CCD, and we might not have the collimator as well. And so this is the SolidWorks model of their system. And you can see the arrows represent the 5 degrees of freedom they have, although one of them is actually completely useless. So our in situ components, so we have one viewport for our CCD and one for the external optics. And so the tunneling junction is right here, and so the emissions will just pass through that lens right there and then go out of the system. The system is at 27 degrees because that's actually the optimal angle for these emissions. And so the first model we have is just a simple system here. It's only got 2 degrees of freedom, and that lens tube right there has two lenses in it for the focusing. So there's not enough freedom in the system, and it's also very hard to cover it for unless there's straight light. And this is the final model that we have, so much more adjustment. There's 4 degrees of freedom in the system, so it works exactly as possible. And it's light enough, and it's basically exactly what we need. And so yeah, it's light, compact, and it's got 4 degrees of freedom. The light, we only operate at about 6% loss after the first lens. And it can be easily adapted. And the normal tunneling current, we get enough photons to do our studies. And so this is the low vibration facility. This was just constructed this summer. It's a shared facility between 3 STM groups at UBC. And the STMs are placed on large granite blocks. These are on pneumatic isolators, so there's all the mechanical vibrations cut out, and the walls have acoustic insulation to make sure that a lot of sound is cut out. And so this is meant to be one of the quietest, noise-free places in the world. And so this is basically the layout of the facility. So the one we're operating out of is the Omega pod in the middle. You can see the massive granite block and the acoustic isolators on the side. And so it's basically just showing you what's going on there. So the spectrum, these are the mechanical vibrations. This is basically the comparison that we go with. And so unfortunately, I don't have the graph with us on it, but we're basically along this line right here with a few resonance beams. So we're only behind, I think it's Cornell. Yeah, it's Cornell. In terms of the quality of our system. And with the sound pressure, we have to get under this green line, and as you can see, basically apart from a few resonance peaks, we're under it. So our facility is exactly what we want it to be. So overall, the tip etching is reproducible for tungsten, and it's a new method, so it's much easier to use than the method commonly used in literature. The optical assembly is workable, it can be adapted, and it can be a standard for future luminescence studies. And the low vibrations facility is what we want it to be. It's one of the best in the world. It's completely noise-free. So I'd like to acknowledge basically all these people, especially the top 2, my supervisor and my lab mates, for helping me throughout the summer and getting me acquainted with all I need to do. And of course, thank you all for listening. All right, any questions?
So you chose those 2 materials, silver and tungsten.
Yes.
So what was the reason you chose those 2 materials? Why didn't you choose any other materials?
Okay. So the silver, I'll start with tungsten. Tungsten is basically the standard. It's what most people use. The other one that most people use is platinum iridium, but they cut it so it's not etched, and so those tips they're never reproducible. You just basically get lucky. But those ones also aren't good if you have, say, bumps in the surface. So we wanted to focus on tungsten for basically regular studies, and if the silver etching didn't work out, we have that fallback line. The silver etching, we wanted that plasmonic resonance because we wanted more photon efficiency. So you get a factor of 10 times more photons when you use a silver tip of the same quality as a regular tungsten tip. So those are the 2 materials we wanted to focus on this time. Anyone else?